Okay, so I've just started the recording. So the idea is that if we have a chain of filters, okay, so with the second order stage plus the second order stage, and this is the first, second, etc. As first stage, no updating. Quite disappointing. Let's see. Okay, now it's working. Okay, so if we have a chain of second order filters, and we have to select the order of these filters. Well, each second order filter will be characterized by a given Q factor. Well, we select the order so that the Q factor of the first stage is less than the Q factor of the second stage, which is also less than the Q factor of the third stage, etc. Okay? In this way, when we have this low Q factor at the beginning, we have the advantage of having a relatively stronger attenuation to the frequencies which are placed in the upper end of the passband region. This means that when a sinusoid enters the first stage and the sinusoid is placed around the cutoff frequency, this sinusoid is attenuated by a factor which is close to minus 30 dB. Okay? So this sinusoid, after the passing through the first stage, is greatly attenuated. Okay? Then the sinusoid enter the second stage, which is also attenuating in the same frequency range. So it is a very weak signal which is fed to the high Q value which has the overshoot. Okay, so the amplification induced by the subsequent stages is somehow pre-compensated by the attenuation of the first one. Okay, if we would have selected the first stage with the highest Q5, the initial input sinusoid would have been amplified by a factor equal to 30 dBs. So quite a lot. Okay, and the risk in this huge amplification is to cross the saturation limit and therefore to induce the distortion. Okay, the op-amp can amplify a signal just in a certain interval. Okay, in which the amplification is indeed linear. If we overcome this interval, then we have the saturation. Okay, so to avoid this saturation effect, one practical rule is to keep the stages with the lowest Q values at the beginning. This indeed is a possible cascade sequence to be applied. This is the case for even order filters, and this is the case for odd order filters. Okay, so in case of odd order filter, you can place the first order stage at the beginning. Okay, because first order stages have no overshoot at all. Okay, so this is quite important fact. This is quite important, especially when you are amplifying or filtering quite high-valued signals, of course. Okay, because indeed saturation is just round the corner. Okay, so to conclude the let's say design strategy for low-pass filter from a pure abstract perspective, the filter design process can be subdivided into these steps. So first of all, you have to select the filter type. So you can pick up Butterworth, Chebyshev strategies. There are many others, such as Bessel filter, elliptical filters. There is a wide range of possible families to be used for this task. Of course, the selection will be somehow related to the filter specifications. So certainly the passband region, the stopband region, the ripple which is tolerated in the passband region, and the minimum attenuation that you need in the stopband region. Once you have selected the family, then you can apply a purely mathematical procedure which allows you to determine the pole position. Okay? From the pole positioning, you have also a way to specify the Q factor and the omega null frequency for each second order stage. Because we have said that the outcome of these strategies are basically complex conjugate pairs of poles. Okay. Once you have selected the pole and zero pairing and the stage sequence, you can start working on the circuit topology. Okay. Actually, the pairing and the gain distribution in particular are tightly related to the circuit topology, because basically we have seen that with the Shannon and key topology, it's much more convenient to have a unitary gain rather than having larger gain to minimize the effect, the sensitivity to variations. Okay, and then you iterate until all the specifications are met. Specifications are not just related to the selectivity of the filters, so let's say the ideal frequency response of the filter, but could be related to sensitivity of variations. And there are also, of course, a lot of other parameters, most important of which is probably cost-related things. Okay, so for example, is your design a low-cost design? So you need, in this case, to use topologies like the multi-feedback or the silent and key, which are based on the usage of single op-amps to implement a second-order transfer function. If simplicity of design and tuning is an important aspect, maybe you can rely on biquad topologies, so KHM or Thomas, because you can tolerate a slightly higher cost induced by the higher number of op-amps in exchange for more simplicity in the tuning of all the parameters. Power dissipation is tightly related to the economic cost, because of course the less is the number of op-amp, then also the less is power dissipation, and so on. Dynamic range is important for the concept that we have discussed just a few minutes ago, in the sense that we must avoid saturation, and therefore Q factor, having Q factor, low Q factor at the beginning of the cascade is better. Noise are also very important effect. We have seen when we have analyzed the op-amp integrated circuit implementation that the noise specification is inversely proportional to the power consumption. Okay, so if we want low noise devices, probably we should trade off a bit of power dissipation to meet the specification. Okay, so the difficulty in the design, indeed, it's to handle all these things together. Okay. If there are no questions in this respect, we can jump to how to use LT-Spice to validate your filter design task. First of all, I want to show you the web page on Virtuale, in which you can find the specification for your design task. So I've dropped a file on Virtuale, which is filter spec 2022, in which you will find a table with your email address, or the email address of students enrolled to this course, and the subsequent specification. So A max expressed in dB, so the maximum ripple in the passband region. A min, 26 dB in this case. The frequency limit of the passband region, 10 kilohertz in this case. The limit of the stopband region, 18 kilohertz. I'm imposing the selection of the Butterworth or Chebyshev family. So basically, if you have a B, then it means that you have to select the Butterworth design strategy. Otherwise, it's the Chebyshev one. Then you have the DC gain specification, and then the possible variations around the nominal value for capacitors and the resistors. Okay, we will see later on how to use this information. Okay, so we have individual specification. If you cannot find your name on the list, please drop me an email, and basically I will assign you the next row of specifications. Okay, so now again on Virtuale, you will find also the op-amp that you will be asked to use in your LT-SPICE specification. These are listed in this script, ideal op-amp.sub. Okay, so you can copy this file and use it directly on LT-SPICE. Please keep attention on the extension of this file. Okay, so save this file as a .sub file, .sub. Okay. Otherwise, you will not be allowed to use this as a library within LT-SPICE. So basically, this is one of the example. So this subcircuit command models indeed the behavior of an ideal op-amp. Okay, so it takes as input the signal connected to node P, so plus and minus, and the node out is the output of the op-amp, of course. Okay. So we will get back to this later. So let me go back to the study material. So starting from the specification that I've just shown to you, the first thing to do is to find the pulse position. Okay, again, applying purely mathematical rules. Then you can choose the filter topology, okay, for each second order stage. One interesting degree of freedom is the fact that for the different second order stages that you will have to implement, you can select different topologies. For example, you can keep the silent and Q topology for the lowest Q stages, and then use the Thomas topologies for higher Q stages, okay, in order to exploit the reduced sensitivity to variations in the Thomas topology. Then you will have to create the op-amp subcircuit as shown on Virtual. Okay, so basically you can reuse the script that I provided on Virtual. From this script, you have to generate an op-amp symbol. I don't know if you remember how we have generated the op-amp symbol for the integrated op-amp that we have designed. Then you draw the schematic, and finally you verify that the specifications are met by simulation. So basically, to verify that the specifications are met, you have simply to run a .ac analysis, because we are interested in seeing the frequency response. Okay, and just a minor variation is induced to the necessity to simulate also the variation of capacitor and resistor parameters with respect to nominal values. Okay, so we will see how to run these, let's say, Monte Carlo simulations. Okay, so to create the op-amp library, let me recall that first of all, it is important to save the file with this extension, .sub or .lib, okay, and avoid placing a double extension like .sub, .c, okay. Then you have to right button click on the blue line here, on the first line related to the .subcircuit command. Then this window will pop up, and you have to select the create symbol tab. Okay, so let me see if I can run it. So right button click, then you go in create symbol, and you automatically create a symbol with this neckpiece. Okay. Okay, the right in my case, I did it in the past, and you get this this automatically designed symbol. You can play with the symbol if you want to change it a bit. Okay, so for example, you can change the appearance of the symbol in multiple different ways. For example, you can cut this rectangular shape and design a new one. You can also move the input port to the classic conventional left position. You can do a lot of changes indeed in the appearance, so the justification can be left-handed, so plus and minus are on this range, and so on. I don't know if you brought your PC with you. If you want to follow me in this activity, you can. Okay, so you can move the output here, etc. Okay, and resketch the whole symbol. For some, then you have to save it, of course, and do all the modification you are interested in. Okay, you can draw a line to generate the conventional triangle shape for the op-amp, etc. Okay. Once you have created the symbol, it is important to edit its attributes, in the sense that you have to go in the edit menu, attributes, edit attributes, and then you have to select the symbol type set. Okay, this is important to use this symbol as to export this symbol and use it in the subsequent design. Okay, once you do so, you can then pick up the symbol and use it to generate more complex simulations. Okay, once you have saved the symbol properly, you will find it in the auto-generated symbols. Okay, so basically, again, if we generate a new schematic, and we go in the component menu, auto-generated, well, we have the symbol that we have just designed. Okay, and then you can combine this symbol in multiple ways to generate whatever configuration you want. Okay. For example, well, this is a DC simulation, not really interesting in our cases. In our case, we are mostly interested in testing a possible variation of the parameters. So this is an example related to nominal value in resistor and capacitors. So you can start by checking whether with nominal values the design is correct. There are several ways to do so with the .ac command. You can either use a simulation like this, or you can use simply the syntax of the .ac command. So one important specification is related to the fact that the filter specifications are provided in terms of frequencies, okay? But please remember the distinction between frequencies and angular frequencies, okay? So most of the computations we did in the study material are related to angular frequency. So please convert this specification into angular frequencies to reapply the same methodologies that we have seen during the classes. Okay, so it's important to avoid confusion between frequencies and angular frequencies. Okay. Okay, let's have a short break, and then after the break we will see the last slides related to the final simulations for this field. Okay, so let's just finalize this presentation. So we have discussed the necessity of realizing a library with the OPAMP description from an ideal point of view, and then use a symbol to reuse the same code multiple times. Okay, for example, to implement the tautomos filter, we can pick up 3 times the same symbol and then connect it, connect all the OPAMPs according to the OPAMP topology that we have discussed in this course. Actually, to further, yes, I was trying to. Okay, so this is the two Thomas configuration. We instance 3 times the op-amp, and then following the conventional topology, we had an input, and we can test the output by running a .ac simulation. Okay, so in the study material, you can find also an alternative and more realistic version of the op-amp, which takes into account the fact that typically the transfer function of the op-amp is characterized by a dominant pole. So the idea is that rather than using a generic topology like this with a resistor, input resistor, very high valued, connected from the positive input and the negative one, plus and minus. Then here we have a voltage control voltage generator, E out. And this voltage control voltage generator, it is connected to the ground, okay, here, and to node out 1. And then from node out 1 to the actual output of the circuit, we have this R out resistor. Okay, R out is very small, just 1 ohm. The voltage control generator amplify with a very high gain, 1 billion. The input at the input voltage between a node plus and minus. So this is the circuit which is simulated with this subcircuit. Okay, it is indeed a quite ideal op-amp with no frequency effect. Then I'm suggesting the use of a different subcircuit, a one-pole op-amp. So in this case, the subcircuit that we are simulating is something like this. We have, again, plus and minus as input nodes. Then we have a resistor which is connected between node plus and node minus. This resistor is our input differential. Then we have 2 common mode resistors connected from node P and node M to the ground. This is input resistance common mode 1, and this is input resistance common mode 2. Then the voltage drop between node plus and minus is used to control a transconductive effect. So we have a voltage control current generator, which is GM. So we take the voltage between node plus and minus, and we multiply this voltage times this transconductance value, transconductance given by this formula. This generates a current. This current flows into this parallel. We have a resistor, R1, and a capacitor, C1. Okay? This node is internal node number 1. Finally, we have an output stage which is realized with a voltage control voltage generator. connected to the ground and to node output 1. Then we have the output resistor, and finally the output node. Okay, so this is what we are placing in this symbol. Okay, we are drawing this with this netlist description. Okay, so my recommendation is to start with this subcircuit. So you generate the symbol for the ideal op-amp. Then you generate a second script with the subcircuit 1 pole, okay, described in this part. And then you test the realization of the low-pass filter with the 1 pole solution. Okay. You may have some difficulties in meeting the specification with this second subcircuit, because this is much different from the ideal one. Okay, and in case you the simulation are completely unreliable in terms of result, okay, then this means that you have to select a different 1 pole subcircuit. How can you change the characteristic of the 1 pole subcircuit? Well, you can either increase the transconductance, or you can change the inner resistor or the inner capacitor. It's like compensating the op-amp. Okay. So once you have used either the ideal or the single pole or both solutions, you can first test the simulation of the frequency response with the pure .ac command. And then, as a last step, you induce variability effect. In this slide, it is shown how you can do that. So basically, the idea is that when you place a resistor in your circuit, you don't give simply the nominal value, but you give as value an instruction. So this instruction is given in terms of this uni function, in which you specify at first the nominal value, and then the possible variation in terms of percentage around this nominal value. Okay, so this uni function is not a library function already described in SPICE. Okay, it is something that you have to describe. Okay, to add a function to SPICE, you use the command .function. Okay, so the function uni has 2 inputs. So the syntax specifies that uni has 2 inputs: the nominal value and the tolerance. Okay. When you provide this function, here it is specified what is the effect. So the idea is that you add to the nominal value a random quantity, because flat is indeed an embedded function in SPICE, which generates a random number around the tolerance value specified by your input. So basically, you take the nominal value, you multiply it by the tolerance, and you get the maximum excursion, the maximum deviation that you can add to your actual value. Okay, so basically, rather than adding a deterministic value, in this way we are assigning a random number according to a distribution which is flat, a PDF function, a probability distribution function, which is flat around the tolerance value, and the maximum value of this probabilistic distribution function is tolerance plus, sorry, this is the nominal value. Nominal. This is tolerance plus nominal, and this is nominal less tolerance. Okay. Well, actually, is nominal plus tolerance times nominal. Okay. The percentage, the 5% more with respect to the nominal value. Okay. This is one way to proceed to test these random variations. Some other cases, rather than using a flat PDF, you can use Gaussian, okay, which is even more realistic. Okay, so the actual values will be most likely assigned to values close to the nominal value, and less likely to the tails of the normal distribution. Or you can use a worst case analysis. Okay, so the worst case analysis is a function which basically has this distribution around the nominal value. You pick up just the worst possible cases. So nominal minus 1% in this case, or nominal plus 1% to simulate the corner situations. Okay. Then you have to use these two commands to repeat the .ac simulation 500 times. Okay. So each time the unit function will attribute to the resistors and the capacitor values random numbers in your specified range. Okay, so you can simply copy and paste these commands to test what happens. Okay, once you test it, you will see that it's quite intuitive. By the way, to add this function, you have to use the edit command, add directive, and you type it. Okay. Okay. Unfortunately, I've shut down LTSpace. So. In the following slides, you will find the instruction and the syntax of the specific commands, but basically you can rely simply in this instruction here. Okay, so if you are interested, this is how you can, for example, compute the Pythagorean theorem with this function, or add extra function. So flat x is a random number between minus x and x, and this is used within the unit function to generate the ideal number. Similarly, you have the Gaussian distribution or the worst case function. Okay, so for example, to implement the 7-order Sallen-Key realization, we have computed in the whiteboard last week. During last week, you can try to realize this circuit. This was the Silent key implementation with the smart strategy, and this was the total mass implementation. So you can try to test all this configuration as an exercise to verify that the simulation are correct, and then you get these kind of both plots. Okay. So this is, let's say, the general idea, guys. Okay, so my suggestion is to test these implementations and run spice to verify that everything is clear. If you have some additional questions, just drop me an email and I will try to help you. Okay. Any questions from the audience? Okay, if not, I think that I can thank you again for the last time for your attention. I will be available today until the end of this class, according to the normal schedule, and tomorrow as well. Let me say that there is also another course associated to this one, the Laboratory of Analog Intelligent Sensor System. Well, actually, Lab of Intelligent Sensor System, which you can select in the second year, okay, in your course schedule. Within this course, we tackle some advanced concept with respect to this one. Let's say the course is not based on frontal classes, but is just based on individual projects. Okay, so at the beginning of the course, I will assign a specific topic to you, and then we will discuss together. It could be also sort of a preliminary master thesis activity if you are interested. Since the Laboratory of Intelligent Sensor System is not based on frontal classes, there is no harm in anticipating the course even in the first semester. So if for some reason you have a more, let's say, busy schedule in the second semester and you wanted to start the activity related to the laboratory with some anticipation, no problem from my side. Okay, we are not forced to be, let's say, fully compliant to the normal time schedule. Okay. Concerning possible master thesis topics, well, in my group we develop indeed intelligent sensor system. So there is an analog signal processing part for the sensor interfacing, but there is also a huge digital signal processing part, because in typical sensor system, what you have is a sensor interface, and then a microcontroller or an FPGA or a similar device to realize things, let's say, which in the end must be connected over the internet or with different radio mechanisms. We are currently working in several application domains, spanning from precision agriculture, for example, or we are currently working in the biomedical field, so to implement wearable sensors. We are also working quite intensively on structural health monitoring tasks. That is, we are working with civil engineers to implement sensor system to monitor the integrity of structures. Okay, this can be done with vibration sensors, because, for example, bridges or rail tracks have some characteristic vibration mechanism which can be compromised when a defect occurs. Okay, so by tracking the vibration modes of these components, you can infer the health status of the structure. Okay, so this is one possible mechanism. Other mechanisms are based on ultrasound monitoring. So in ultrasound monitoring, this means that we actuate an elastic wave within a medium, and we receive a possible reflection or anomalous echoes to infer again the integrity of the structure. There is a huge variety of situations in which the sensor deployment can increase a lot the safety of these structures. So there is a huge interest now in developing this system. We are actually currently collaborating with RFAI, which is an Italian company, basically the one which controls all the rail tracks in Italy. Okay. Another industrial relationship we have is with Eni, which is an Italian oil and gas company, because also for oil and gas infrastructures, it's of the utmost importance to control the integrity, prevent leaks, especially for huge storage tanks. So, and in all these fields, what is necessary is to deploy huge networks of, let's say, affordable sensors. Okay, so low-cost sensor which can be deployed in very large numbers. Okay, so sensors means again the actual transducer, the sensor interface, the microcontroller. I don't know if you have ever programmed microcontrollers like STM32 or device similar to that, but you will see some other courses in the next semesters, so you will get the gist of it. Okay, and this can be eventually combined also with artificial intelligence algorithm, because what you want to do is to extract indeed an alarm. Okay, so when there is an anomaly, the signal is somehow different with respect to the pristine one, and then you have to find an automatic mechanism to send the alarm, because you cannot send all raw data, otherwise the network will be compromised. Okay, too many data, you cannot send too many data to a central processing unit. You have to bring the inference to the extreme edge. Okay, in the computation. Okay, so feel free to contact me if you are interested in this kind of thesis topics. I've seen that many of you have filled the form related to the iOS symposium, so I will be pleased to meet you in that occasion. And again, thank you very much for your attention.